Hi, good to see that you've made it to Module 3. My name is Robin de Kruijf, and in this module we'll dive into the world of radionuclide production. You have already learned about radiation, radionuclides, radioactive decay, and how these principles are applied in radionuclide generators from my colleague Antonia Denkova. We have seen that the radionuclides obtained from a radionuclide generator can be used to image or treat patients in a hospital. Typical medical radionuclides are, for example, iodine-131, lutetium-177 for therapy, and fluorine-18 or technetium-99m for imaging. These radionuclides are injected into the patient as radiopharmaceuticals, where they travel to the tumor site. Once at the tumor site, they can be used to image or destroy the tumor. But where do these radionuclides come from? In this lecture, we'll take a look at all three types of production facilities: research reactors, cyclotrons, and linear accelerators. When we take a look at this cutout from the chart of nuclides, we find the stable isotopes in the center, here in gray. To the right-hand side of them, we find the neutron-rich radionuclides. These typically decay by emitting a beta- particle and are therefore used for therapeutic purposes. These are often produced in research reactors through neutron capture reactions. Examples of neutron-rich radionuclides are molybdenum-99, iodine-131, and lutetium-177. On the left-hand side of the stable isotopes, we find the proton-rich radionuclides. These are generally produced in accelerators, such as cyclotrons and linear accelerators. They can decay, for example, by emitting a positron, and can then be used to image a patient using positron emission tomography, also called a PET scan. Examples are carbon-11, fluorine-18, and astatine-211. Research reactors are typically used to produce the neutron-rich radionuclides. Their design differs from nuclear power plants because they are optimized for neutron flux, not for the generation of thermal and electrical power. The neutrons that are produced in the core of the research reactor by the fission of uranium fuel can be classified based on their energy into thermal, epithermal, and fast neutrons. The thermal neutrons are generally preferred for radionuclide production. To irradiate a target in a research reactor, it needs to be packed in an irradiation container. For short irradiations, these containers are often made of polyethylene, a type of plastic. Because this material is not very resistant against radiation and starts to break apart at higher radiation doses, quartz ampules are generally used for longer irradiations. The plastic containers, also called rabbits, can be transported pneumatically to the reactor core, whereas the quartz ampules are often transported mechanically. Proton-rich radionuclides are often produced using a cyclotron. The ions with which the target will be irradiated, usually protons, are released from an ion source in the center of the cyclotron. A magnetic field is then used to accelerate these ions until they have the energy required to produce the radionuclide of interest. The ion beam is then extracted from the cyclotron to irradiate the target material. Finally, linear accelerators, or LINACs for short, are also used to produce radionuclides. Their working principle is actually similar to that of a cyclotron, but rather than accelerating these ions in a circle, they are accelerated along a linear trajectory. These LINACs can become very long, from several meters up to kilometers in length. Next to protons, LINACs are also used to accelerate many other light and heavy ions. And a special type of LINAC is the electron LINAC. An electron LINAC accelerates negatively charged electrons, which interact with the converter material to produce high-energy gamma photons. These gamma photons are then used to irradiate the target material. We call the production route where we use photons to produce radionuclides photonuclear production. When using an accelerator to produce radionuclides, the target material is placed in a special containment, which is also called target. This target can be made of different materials, such as aluminum or tantalum. When you are radiating a solid target material, the material is loaded into the target containment either pneumatically or mechanically. Fluids or gases are generally transported using tubes. If you want to produce a specific radionuclide, there are a few things to keep in mind. Of course, you do not want to produce any other radionuclides at the same time, because that would decrease the quality of your product. However, you also need to keep in mind how your target material might behave in an irradiation field. Does it stay stable when heated, or does it undergo any chemical reactions with the containment material? And then there's also the potential of radiolysis of the material, which means the damage done due to interactions with ionizing radiation, which could, for example, break it or cause gas formation. Reactors, cyclotrons, and LINACs all have their advantages and disadvantages when it comes to radionuclide production. For example, while you can irradiate quite a number of samples in a research reactor at the same time, reactors are not available everywhere, and they produce a relatively large amount of nuclear waste. Cyclotrons, on the other hand, don't have such a large waste problem and are often locally available, but they have the disadvantage that you can only irradiate one sample at a time in a relatively small irradiation volume. Looking at the advantages and disadvantages of linear accelerators, you'll see that these are quite similar to those of cyclotrons, although their availability depends on the type of linear accelerator. In the end though, the radionuclide you want to produce is often the deciding factor. Is it a neutron-rich or a proton-rich radionuclide? We have now learned about the different facilities that can be used to produce radionuclides. In the next lesson, we'll go one step further. We'll learn how to calculate how much radioactivity you can produce and on which factors it depends.